Let us continue our review, and this time let's do a couple of problems related to the complex integrals. So this is our problem number 3. Number 3, and let's write it down. I will underline, and this will be let C be a simple closed contour bounding an area S. Prove that the following equalities hold. So we have the first equality. Here we'll take the integral over C and integrate the x dz, that's a complex integral, along this contour, and the answer is that this is I multiplied by S. That means this is the measure of the area bounded by the contour C. And B is again the contour integral C. This time I take y dz, and this will be equal to minus S. And finally C, and here we'll take again integral. This time I take z conjugate and put here dz, and this will be equal to is. So this is our problem, and let me underline it and write it down. Solution. This problem is just to remind you that our integral, complex integral, that means if you have a complex function f of z is equal u of z plus I v of z, v of z, then this complex integral C, and let me write it down, u plus I v of, and this is dz, can be written as two line integrals. So those are the oriented line integrals, second type, vector value. So for the vector valued function, so this will be first line integral will be C, and then we have here just simply u dx. Oh, sorry. Maybe rewrite it down like this, please, plus iv. This will be better to just remind you that there is a simple way of memorizing it. So let me move it a little up, then this will be equal, and here we have that this is going to be integral. Let's move it. So this is u times dx, so this will be u dx, and I times I is minus 1, so let me show you how it goes. So first we have here this times this, and this times this. It is for the real part, so that means this will be first part, and this will be minus, and this will be vy, so that's the first integral, line integral. This will be I, and this will be C, and then we are getting here the second one. So here we are getting here that we multiply differently. That means we have here this multiplied by that, and by that, and this one by that. So we are getting two terms, and in this case it will to be, so which one is dx? So this will be v dx plus u dy, the second line. The second thing that we are supposed to remember, So this is related to, this is a line integral, and this is also line integral, second type line integral. This is second type line integral. And the next thing we should remember is the definition, not the definition, is the so-called Green's formula for the line integral. So this is the Green's formula. And the Green's formula in our case, so suppose that the boundary of the region is exactly the C, so that means this is the region, this is the region. This is constant C, sorry, this is curve C, the positively oriented boundary of the region G. Then we have here that if you take the line integral over C, and this will be P dx plus Q dy, so this integral is becoming double integral over G, and here we are having here that this will be dq dx minus, and this will be dp dy, bracket dx dy. So that gives you on the right hand side double integral. So we will apply this particular formula to the line integrals above. So what do I get here? So let me write it down. A, if we write it down, the C, and this is x dx, so rewrite, sorry, dz will be equal, so write it down, this is cx, and this will be dx plus I dy, which gives you two integrals. First one is x dx, and the second one is plus I, and this one is x dy. And by applying this Green's formula, so to the number 1 and to the number 2 twice, we obtain, in this case, that this integral is actually equal to integral, and I'm getting here double integral over my region G, and here we are getting this is equal, so there's only one function, so clearly this is 0 times dx plus 0 times dy, all the partial derivatives of x. So here with respect to, so with respect to the y must be 0, and the other function is 0. So then I have the second one, write it down, g, and here that's the dx, we have here 1 because this is equal to dx dy, and that one is equal again to the dx dx. So the other one is of course 0, so you are getting that this is I, and this is double integral g dx dx, and of course this integral is just measuring the set A, so that means this is equal to times s. So measure of the g is exactly s. This is the area. So let's do the b. Similarly as we did before, we are getting here that this c and this is y, and put here like this again, dx plus I dy is again equal, this is c, and that one is equal to y dx plus I, and then you have here c, and this will be y dy. And of course, by applying the Green's formula, we obtain again that this one, so this one is equal double integral over g, and here this derivative with respect to y, so this will be minus, and this will be, this is q, so this is minus, so it will be the second term, so this will be dy dy, and this will be dx dy, and plus 0, then the second integral is just simply 0 over g, this is 0 dx dy, and since that one is equal to 1, by exactly the same argument as before, we are getting here minus s. We are getting here minus s. And let me, okay, I actually have more space here. Let me do the case number C. And here we have here that integral C, or put it like this, z bar dz is equal, so let's rewrite it. This will be x, and this will be minus iy, and this will be dx, and this is a plus I dy, which will be equal. Let's separate the real parts. So I'm getting here, this is x dx, and the second one is here. So you can see this is plus y dy, and this one will be plus I, and the imaginary part will be simply x dx. So this will be minus y dx, and this will be plus x dy. And now apply again the green formula. So we are getting double integral of g, and what do I get here? Dx, so this will be dy, and this will be dy dx minus dx dy, and this will be dx dy. Of course, this is both are 0, so we are getting this part is 0, and this is plus I, and this is double integral g again. And I have here the first one is, so this one is this one with respect to x, so we are getting dx minus, and minus is plus dy dy, and this will be dx dy. And since this one is equal to 1, that one is also equal to 1, we are obtaining again that this is equal to I integral double integral over g dx dy, and everything is equal to I, and again the area S. So we obtained the first problem. So let's go and let's do the second problem. Let me adjust the position. One more time, trying to click properly. Yes, and then this time I move it correctly to the beginning. And let me do the problem number 4. There is my problem number 4. So the problem number 4. Evaluate the integral the following integral. So the integral is like this. C is a contour, we'll describe it in a moment, Zn, and this one is log, this one is z, and this will be dz, but where C is equal, and let's write it down, this is EIT, and now we assume that T is the contour that starts at this position and ends in this position. Okay, let's do it for exactly this contour, exactly this position. So it starts here in 0. So maybe go back. Do it first this way, minus pi and pi. And then I need to make a picture. So solution, and let me do the picture here. So in order to do a picture, I need to do kind of draw some drawings. So let me first draw the coordinate system. So we have here coordinate system. Let me put it like this. This is my first coordinate. Too big. One more time. Good, and then let me 1 second. So we have the first coordinate. Let's put the second coordinate. And again. Oh, we got here that one. Very good. And then let me make sure that we can continue. So let's simply merge it. And then now no. So in such a case I can continue. So go to the black one, please. Let me continue. So here we have the first coordinate, here we have the second coordinate. And of course what we are doing here, we are understanding that here we have here kind of a notion of the logarithm. So in our case we have to remove this line, because what is this logarithm that we are talking about? Put it clearly, log of z denotes the principal branch of logarithm of z. So that means we have to remove this line. That's our removal. We remove, and we assume that we have here a contour, which is the circle. Here is the circle. So let me draw this circle now. So I will put it here, and let me draw this circle, and the circle looks like this. So we have here this our circle. And remove the selections, and we have the path of the integration. So notice that our logarithm is practically, you can say, discontinuous at that point, but this is our sorry, this is our beginning point. Our curve actually starts at that point, and we go that way. So this is a point which corresponds to t is equal to minus pi. And then we will arrive, and that point is exactly minus 1. This is 1. And this, when we arrive, this will be t is equal to pi, and we'll be arriving from that side. So of course this function logarithm is not analytic on this whole circle, but you can think about it that here you can use your scissors, you can cut this plane. Like take the scissors, you take the scissors and take the scissors, and you cut your plane in the two separate portions. Open it here. So once you open, you can think about it that this curve starts here, goes there, and the endpoints in certain way are not related. You will just go accordingly to the branch. So first thing what you need to do is the following. So assume that we need to use some kind of a result. So what is the result that we need to apply? In such a case, you can say that, probably I need to use here the fundamental of theorem of calculus. If my function f of z is equal to the z to the power n, and this one is equal to logarithm of z, so How to find f prime of z is equal to f of z. So what is my f of z, capital F of z? So that means what is my antiderivative of the function f of z, small f of z. So in order to find this antiderivative, maybe you should just remember how it was done in the calculus of single variables. So let me write it down. So if you remember, this would correspond to this particular expression. So this would be your antiderivative of the function x n ln x. And we know that you obtain it by integration by parts. So you take n plus 1, and this will be n plus 1 ln of x. And this is minus, and you take the n plus 1, and then you are getting here the integral from x n plus 1 times 1 over x dx. And of course, that leads to this expression. Take this n plus 1 outside, and then you have here x n plus 1 ln of x minus, and this will be 1 over n plus 1 and x n plus 1. Why? Because here, of course, this one cancels that one, and we are getting the same integration. So that is my antiderivative for that function in the real case. For, of course, this is for n different than minus 1, and if this is equal to the 1 minus 1, so this antiderivative in such a case, it is clear to, that's very easy to notice. This is just simply 1/2 ln square of x. Of course, I will just put here c if you want to put here c. Okay, and now those are the formulas. So that means simply, if this is the formula for the antiderivative in the case of real logarithm, probably, most surely, this is also the same formula for the antiderivative in the case of complex logarithms. So in such a case, my f of z is equal, and we have here two formulae. If n, sorry, I don't know yet, so we just copy it 1 over n plus 1, and here we have here z to the power n plus 1, and this is log, this is this branch of the logarithm, so this is log z minus, and this is again n plus 1, and this one is z to the power n plus 1. N plus 1. Actually, I could simplify it. This is for n different than minus 1. And in bottom, I have here this one is equal 1 over 2, and that will be log square of z if n is equal to minus 1. So therefore, we can just simply use this picture as the guidance, and then simply write using the fundamental theorem for complex integrals that the integral over c, and write it down for n different than minus 1 of z to the power n, and this will be log of z dz is equal, copy the antiderivative. Actually, I will put this n plus 1 here, n plus 1 here, and here I will write log of z minus, and then this will be 1 over n plus 1 here. And then this must be taken from the point minus 1 taken from the, and that one is from the negative side, and then point of minus 1 from the positive side. So what does it mean? So that means we go here. So in this point, that point means simply that here of this logarithm of minus 1 will be equal minus I pi. On that side, log of minus 1 will be equal to I pi. So that's the difference. So that's the difference. So this is the arrow. So that's the difference. So that means we understand that everything except the value of logarithm will be the same. So I can just plug it in, And I'm getting here, this one will be basically this is minus 1 to the power n plus 1, divided by n plus 1. And then, of course, I have here also that this will be equal to log, and I put here like this, minus 1 from the negative side. So I put here, let's say, sorry, positive side. Maybe let me write it more nicely. From the positive side, and this will be minus log from the negative 1. Sorry. From the negative side, and this part will be the same, so it will be just simply minus 1 plus 1. So this will be eliminated easily. So let me put it minus 1 n plus 1 plus 1 n plus 1, and that is this is 0. So we can now continue, and we are getting here, this is minus 1 n plus 1 to the power n plus 1, and here that one is equal. So what is the value of this one? As we notice, this is pi I, this one is minus pi I, so we are obtaining that the value here is 2 pi I, and that's the answer for this particular integral. So this is the first answer. And the second answer, if n is equal to minus 1, then this integral c, and this will be zn log of z dz will be equal, take the antiderivative, so this will be 1/2 log square of z, and then you just simply, so that's minus 1, so just simply, maybe I should simply write it down, this is minus 1, so that is equal, and you are getting here the following value, so this will be equal 1/2, and this will be log square of 1, and this minus 1 from the positive side, minus log square minus 1 from the negative side, but this is square, so you are getting this is equal 1/2, and here we obtain this is I pi square, and this is minus, and this is minus I pi square. Of course, they are giving 0 because they cancel each other. So we got the answer. We got the answer for this integral. So we should understand that in this case, the logarithm was chosen to be. So logarithm was chosen to be principal logarithm. That means we have here the logarithm that the domain of this logarithm was obtained by cutting the plane at this particular location. So we make a cut and we consider this, let's say, these two pieces, that piece, and so this is positive and negative piece, to be separated, not connected. This line was removed by the scissors here. So this is kind of an easy way to see it. Maybe for you, just to show you that in this case, if you choose a different, let's say, part of, let's say, beginning of your path of integration. So for example, if C will be given like a E, I, T, and this is the change, and alternatively, if C is equal, and this will be IT, so this is I belongs to 0 to pi. So in such a case, our picture will be a little different. Let me use the hand to draw it, so I don't want to waste my time on the drawing. So this is my point 1, and this is the beginning of the path. So in such a case, this is the path of integration. This is the circle, and we just remove that line. So our logarithm is starting here, and we assume that our logarithm, this logarithm that we are studying here, is kind of a log, writing down log of z. So we assume still that at that point it will be the log of 1 will be equal to 0, but at that point here the log of 1, so this is positive side and this is negative side, will be equal to 2 pi i. 2 pi i. So this integral is actually different, so we can say that if I want to apply again the fundamental theorem, and this what we are doing, just simply write it down, logarithm of z, this is a different branch of logarithm, divided by z dz. Still we are getting the same antiderivative. This is not nice. Maybe log 1/2, and this is again log square of z, and here we are taking it. I didn't write it clearly here. So this will be -1. So this is -1 negative and -1 positive. So this is exactly opposite, because you start at 1. So you start at 1 and you end. So this will be you end at 1 from the negative side, and you start at 1 plus on the positive side. So positive side is here, and negative side is here. So now you can rewrite it. And what do I see? So logarithm square of 0 is 0. So you're getting here that this gives you 2 pi I. So this is 2 pi I square minus 0 square. And this gives me exactly 2 pi square minus. So this is 1/2 4 pi square I square, which gives me minus pi square 2 pi square. Minus 2 pi square. So this example actually shows you that with the logarithm, with the function logarithm, the choice of the beginning of your curve, in the case when you do not have a continuous branch along whole curve, because you have this discontinuity of the logarithm at the at the beginning point. That means in this case your function, your logarithm must be chosen accordingly to the beginning of the curve. So you see, the choice of the beginning point of the closed curve may lead to a different result. Before we had 0, now we have minus 2 pi square. Clearly that indicates that this kind of the let's say analysis is important to be done very carefully. It is sometimes easy to make mistakes just by writing formulas without understanding the situation that takes place. So let me look again. Do I have anything here? Oh, we did it already. So maybe because I do not have let's say prepared enough space for the next problem, so maybe we finish this example now, and in a moment I will write maybe 1 or 2 more additional examples for this review, so you will have sufficiently, let's say, enough material to refresh your memory regarding the complex integration. In this case, complex integration, and Cauchy formula is coming. Thank you. So that's it, and see you in a moment.